Hi everyone, we're Group 16 and our project is AI Insurance Stress Test, Agricultural Insurance Subsidy and Pricing Policy. Over the next 15 minutes, we'll walk through the economic problem we're solving and the AI model and system we built, and a live demo of our working prototype. Let's start with why this matters. Climate change is no longer a tail risk, it's the new baseline. Extreme weather events are becoming more frequent and more severe, and Taiwan's agricultural sector is directly exposed. Traditional crop insurance is priced using static, historically calibrated actuarial tables, but those tables were built for a climate that no longer exists. As risk becomes more volatile and nonlinear, static pricing breaks down, premiums become either too expensive for farmers to buy or too cheap for insurers to stay solvent. This is also a real policy decision happening right now. The government has to decide how to subsidize agricultural insurance premiums, and that decision has direct fiscal consequences. So our goal was to move beyond a theoretical exercise and build a tool that could actually inform that decision, balancing farmer protection against government fiscal discipline. So our project is built around four economic inefficiencies that map directly onto our course framework. First, it's market failure. Climate change is a negative externality that insurance can't price away. When catastrophic losses become correlated across an entire region, private insurers face existential risk and may simply exit the market. A model literally computes an insurer market's exit probability to quantify this. Second is informational asymmetry. The government cannot observe how much effort each individual farmer puts into loss prevention, irrigation, maintenance, crop choice, drainage. When subsidies rise, farmers' skin in the game falls, and realize claims rise faster than the underlying risk would suggest. This is a classic moral hazard problem, and we model it explicitly with a moral hazard coefficient. Third is transaction cost. There is a persistent gap between the actual fair premium and what farmers are actually willing to pay. Our model captures this with a take-up function. The lower the net premium, the higher the take-up, but it never reaches 100% because of this friction. And fourth is the empirical gap. Linear historically, loss tables completely miss the catastrophe region. The nonlinear jump in losses once climate stress crosses a threshold. This is exactly the gap that Monte Carlo simulation is designed to close. So these four problems map onto four pieces of economic theory that drive our model. First is Pythagorean subsidy logic. Since climate change is a negative externality, the subsidy rate S is the policy lever that internalizes that externality and pushes insurance take-up back toward the social optimum. The second one is social cost of public funds. Every dollar or NT dollar of government subsidy doesn't cost society exactly $1 because taxation itself has deadwood loss. We set lambda equal to 1.3, so our optimization doesn't just maximize farmer welfare, it maximizes farmer welfare minus lambda times the fiscal cost. This is the direct link to the optimal income taxation unit in our course. And next, risk aversion and certainty equivalence. Farmers are modeled with CRA utility, constant relative risk aversion. The welfare gain from insurance isn't just the expected payout, it's the difference between the certainty equivalent income with insurance versus without it. That's the value of converting a volatile income stream into a stable one. Moral hazard interacting with fiscal value at risk. As subsidy rises, claims rise faster due to moral hazard. So a policy is only fiscally feasible if the variance of cumulative discounted government transfers stays under the budget cap. So how do we actually build this? We chose a dynamic Monte Carlo grid search over candidate subsidy rates from 0% to 80%, rather than a closed form formula or a black box deep learning model. Here's why. One is to combine a nonlinear catastrophe regime, a logistic take-up curve, CRA utility, moral hazard, and a variance constraint. There's no closed form optimal anymore. A roughly 17-point grid search is cheap, fully transparent, and fully auditable, which matters enormously when you're producing a policy recommendation, not just a prediction. On top of that engine, we built a three-stage agent pipeline. Stage 1 is simulation agent. That's the Monte Carlo engine itself, producing welfare, fiscal variance, take-up rates, and exit probabilities for every candidate's subsidy rate. And stage 2 is the retrieval agent, a pure Python TF-IDF retriever that searches our knowledge base covering Taiwan's institutional context, the Dutch and EU benchmark, and the underlying economic framework. And stage 3 is the policy writer agent. This takes the simulation output plus the retrieved context and drafts a structured 5-section policy brief using GPT-4o with a template fallback so the system always works even offline. So this is the outlook of our Streamlit application built on Python. So this entire pipeline runs inside an interactive Streamlit application. Let me show you live. So on the left, you can see every parameter of our model: the climate stress trend, loss volatility, farmers' risk aversion, and the social cost of public funds, and the moral hazard coefficient, the fiscal budget cap, and the shock multiplier for stress testing. These all map directly to the economic concept we just discussed. And let's run the simulation with our baseline assumption. This runs a 2000 Monte Carlo path over a 10-year horizon for every subsidy rate for 0 to 80%. And this model recommends a 70% subsidy rate, and importantly, it tells us this fiscally feasible under our budget cap. And these three charts shows what's happening across the full range of subsidy rates. On the left, this chart shows social welfare, farmer welfare gain minus lambda times fiscal cost. Across every subsidy rate, welfare rises the whole way across the grid, which tells us the binding constraint isn't welfare at all, it's fiscal. And our recommended 70% rate is the highest rate that's still consistent with the variation 95 budget cap. If the government were willing to accept a higher fiscal exposure, this curve tells us welfare would keep climbing. And in the middle, here's the fiscal constraint directly. At our recommended 70% subsidy, the expected fiscal cost over 10 years discounted in about 4,000 million NT dollars, and the 95 percentile variation 95 is about 4,652 million, just under our 5,000 million cap. This operational fiscal discipline as a hard constraint, not just a talking point, and is consistent with the design of Taiwan's existing agricultural insurance fund as a backstop. And on the right, this is where information asymmetry becomes visible. As the subsidy rate rises, take-up climbs from near zero to about 27%, because the net premium farmers pay falls to what they're actually willing to pay. But insurance market exit probability rises right alongside it, from about 15% to 46.5%, because moral hazard pushes realized claims higher. This is the core tension. The privately optimal subsidy for any individual farmer would be 100%, But the socially optimal rate, once you price in moral hazard and fiscal cost, is much lower. And below that, we run a separate stress test. What happens if the climate shock accelerates by 50%? You can see the distribution of required government transfer, with variation 95 and variation 99 marked. Even under this more severe scenario, we stay close to our original estimate, but the margin of further shocks is thin. And just to show this is a real interactive tool, let's increase the moral hazard coefficient and run. So we can notice that the recommended subsidy rate and the exit probability shift in response. The model is generally dynamic, not a static lookup table. Last but not least, how do we make sure the AI doesn't just make things up? Our policy writer agent is governed by a strict system prompt with two key rules. Rule 1, you may only use numbers from the simulation results and the retrieved context. It cannot invent statistics, laws, or institutions. Rule 2, if the retrieved context flags a figure as illustrative, the model must describe it as illustrative or indicative, never as an official statistic. We also enforced a fixed five-section structure: headline recommendation, economic rationale, international benchmark, fiscal risk flag, and a caveat about model limitations. So the output is always policy brief blend, not a rambling essay. And if no API key is available, the system falls back to deterministic template using the exact same structure, so the prototype is fully operational offline. A full prompt iteration history from a naive version 1 to discovered version 3 is documented in our prompt appendix. And this is our prompt appendix. To wrap up, our model recommends setting the agricultural insurance premium subsidy rate at approximately 70%, a rate that is physically feasible under a 5,000 million NT dollar variation 95 budget cap. And that happens to align with the EU's own 70% co-financing ceiling under the Common Agricultural Policy. But two things have to come with it. First, because the insured exit probabilities remain near 46.5% even at this rate. The agricultural insurance fund must remain in place as a backstop. Second, because moral hazard rises with the subsidy, we recommend pairing it with conditional requirements like irrigation or drainage standards to limit the drift in realized claims. Longer term, the next step would be moving from a constant subsidy rate to a dynamic, time-varying policy path. And this is our presentation. Thank you for listening. Hope you like our project.